I don't know. Okay, I guess we are starting. Okay, Ishan, are you ready?
I'm ready.
Okay, let's go. Excelente. All right, that's our workshop 4 on machine learning.
So other than this, so this is basically what's in PowerPoint.
Yeah.
What else? See you guys.
Excuse me? Do you mind?
So light up one when you're allowed, and also have red when you can't take. Yeah. Don't use the street for the teach the to get crossed out and then light up the one you can't take.
Every single course you're going to take is starting now in your 4 years.
Yeah, elective, that's when I got into after
Yeah, sorry.
Oh,
for like electives,
it's-
because you see these things are like electives.
They're already lit up.
They're lit up too.
Because they're the same as freshman courses. Okay, guys. Is everybody what of the people who are here, who is here, who is interested in like hearing me talk for a while about neural networks? Is that why you guys are here? Okay, you're reasonably somewhat interested. Okay, I'll try not to be super boring. By way of introduction, my name is Ishan. I work at a company called MetaMind. We're a small company in Palo Alto, where we build algorithms to solve artificial intelligence and machine learning problems. This means that in our day-to-day work, a lot of the time we work with neural networks, which are a specific type of machine learning model that I personally think are really cool for a number of reasons. Hopefully by the end of the hour, I will have given you some sense of why I think they're cool and maybe just a little bit of intuition about how they work. I'd also like to try to be a little bit hands-on about this, and my definition of hands-on in this case means code. Are just by way of a show of hands, do any of you know Python here? Okay, so you're all reasonably, that's actually really, really good. Are any of you, so I guess the way this is going to work, since this is a fairly small group, is I'm going to be doing code, and I'll try to do my best to explain it, but if at any point during stuff I'm talking about or stuff I'm coding, if any of you have questions, like, please somehow get my attention, because I will not know when I'm not making sense and when I am. Please, like, cut me off, interrupt me, do whatever you have to. It's a small enough group that it really doesn't matter. So without further ado, I guess I'll get started. Oh, by the way, one more question before how many of you, if any, were at the other machine learning talk a couple hours ago? All right, 2 of you. So I'll try not to assume too much. So these are a bunch of pictures and a bunch of captions, and these are actually results of a neural network that a researcher in Stanford made a couple years ago, actually, whose job is to classify images and to generate captions of them. So basically, this guy at Stanford built a model, a computer program, that given nothing but an image, can sort of figure out what's actually going on in the image, not only in terms of like what the image contains, but what is, for instance, it can figure out in the first picture that there's a person, that there's a black shirt, that the person is wearing the black shirt, that there's a guitar, that the person is playing the guitar. And it knows enough about the relationships between people and objects and things, and enough about human culture to figure out that a man in a black shirt is playing guitar. It also knows enough about the English language to be able to synthesize that into a sentence. Likewise, for the other pictures, we have construction worker in orange safety vest is working on road. Girl in pink dress is jumping in air, black and white dog jumps over bar. That's a pretty high level of complexity if you think about it. If any of you guys have done algorithms before, literally the only input data we're giving this algorithm is a series of pixels, which is just like a big grid of numbers. And from that grid of numbers, it has to figure out levels and levels of complexity. It has to figure out patches of color and shapes and edges and simple shapes in terms of those edges. It has to figure out features. It has to figure out texture. It has to group objects. It has to figure out what those objects actually are. Not only that that is a person, but that that is a girl, like that is a young female person, that she's in the air, that she's jumping because there's a sky behind her and there's a certain distance to the ground, that like when you see little girls in the air, that the action that they're doing is called jumping. And what's cool about all of this is it figured it out entirely on its own. That is to say, the model knew nothing about English language or people or actions or pictures or image processing or any of this. Literally, one of the beautiful things about neural networks is that they learn in a way that's sort of vaguely similar to the way we do. That is, rather than being taught rules, you just feed them a bunch of examples and they can infer relationships between data. The thing that makes neural networks specifically so powerful is that the kinds of relationships they can infer tend to be incredibly, incredibly complicated relationships. Whereas, say, linear regression or some of the forms of clustering that were in the previous talk can figure out like simple correlation stuff that you can plot on a graph and reasonably see like, oh, look, there's a line here. Neural networks can, fundamentally, they're just figuring out correlations, but they're figuring out correlations that are so indirect and so involved that it looks like intelligence, basically. Here's some more examples of what neural networks these days are capable of. And the idea is that hopefully we'll build up to something that's sort of close to this level of complexity. But given an image, this is a deep neural network that was trained to come up with just a label for what the biggest, most important part of the image is. You can see here it did pretty well. You and I would notice maybe in this image, you would notice the people, but the specific data set that it was trained on didn't include labels for any of the people. So it picked up like this thing over here is a motor scooter. And that's pretty good, right? That's in fact the correct label. And you can see below that, its next four most probable guesses were also like pretty decent guesses. If not a motor scooter, it was either a go-kart, a moped, a bumper car, or a golf cart, all of which are sometimes visually and also sometimes semantically related things. So this is a pretty powerful model that it was able to figure that out just from pixels. This next one, apparently the correct label there is grill. The neural network thought it was a convertible. Pretty plausible error. If I looked at that, I would think that was a convertible. And then that last example, the correct label was in fact cherry. The neural network, I don't know, stupid model guessed Dalmatian. No idea why it would do that. But you can see these are pretty sophisticated models, and this is actually basically at the cutting edge of what computers are able to do in terms of artificial intelligence and machine learning. And hopefully we'll try to build up to a little bit of that. But before we do, one more demo I want to show you. And this was a group of researchers at a company in London called DeepMind. Recently came out with this neural network, which they were able to teach to play simple Atari video games. And this network, just like all the other neural networks, was given no prior information about the rules of the game. It was given literally nothing other than access to the controller, so it could push buttons and stuff. It was given the raw pixels on the screen of the game, and it was told that the score is in the upper left-hand corner, and you want to make that score go up. And given nothing but that, we can watch here as the neural network actually sort of figures out how to play Breakout. You can see after a little bit of training, it's like still pretty bad. It doesn't even seem like it's trying really. But after another 100 examples, it's sort of picking up on the basic game mechanic here. After a bunch more, it's now like not the greatest player, but I mean, it's certainly, I wouldn't call it bad at this point. It's making progress.
Better than me.
Yeah. So this is where cool stuff happens. Take a look as this algorithm it's just going to try a bunch of random stuff. And then at some point, it comes upon this strategy where it tries to like shoot the ball up behind the thing and get it stuck on top of the bricks. And from that point on, this is basically an expert level breakout player, because once it figures that out, you can see it basically just like destroys this game. It's pretty great. Anyway, this is all to give you guys some small level of intuition on how these things work. Basically, they just try a bunch of stuff, and eventually they pick up on what works and what doesn't. And when they figure out what works, they remember that. So I said I wanted this to be a little bit of a hands-on thing, and that I want to give you guys a little bit of understanding in how this stuff is actually implemented. Hey, what's up?
Is the practice of feeding raw pixel data like common, or do you usually like, is it like considered like super advanced? Do you usually like tokenize input, tokenize like images into some like super pixels or something, and then feed that into the network?
It depends on exactly what you're trying to do. When you're trying to do image processing specifically, so in this case, right, it was sort of a trivial example because we're teaching a computer to play a video game that we already know the rules to. And if we wanted, we could very easily feed it, like, we didn't have to make the neural network do all the hard work of deciphering the pixels in that game because we already know what they represent. But with things like real world pictures, like all of the winning convolutional networks today are trained very directly on raw pixel data. So you take the pixels, you like maybe crop them into a standardized size, and then you feed them directly into the network. And what's beautiful about this, I'll probably go into this a little bit later, is the network will learn sort of like the same pre-processing steps that you might normally do, like feature transforms, histogramic gradients, stuff like that if you do computer vision stuff. The neural network will learn its own versions of those, and its own versions of those will tend to be a little bit better suited to the specific training data you give it than any generic thing. Okay. In general, it's considered a desirable characteristic of a neural network model if it can process data with very little pre-processing. The answer, though, like, it entirely depends on your use case. If there's pre-processing that you can do that makes it much easier for the network to learn, then you should do it. But the cool thing is, like, because these networks are able to learn very indirect correlations, most of the time they will figure out any necessary pre-processing on their own. Anyway, so I'm actually going to completely switch tracks and jump into code right now. Because what fun is any of this if not for code? Just for reference, by the way, are any of you right now planning on following along? If so, I'll try to be a little bit. Okay, cool. So I think this was mentioned in the notes for this lecture at some point somewhere. But if you're planning on following along, it would be really helpful if you have a Python library called Theano installed.
Yeah.
Any chance either of you have that? No? All right. I'm going to go through the installation instructions for Theano then. Shouldn't be too hard. Actually, I think you should basically just be able to do pip install Theano. And in my case, I already have Theano, but in your case, that should basically do it if you have NumPy installed already. Let me know if you run into problems with that. But having installed Theano, I'm going to go ahead and create a little file. And so Theano is, by the way, basically a library that lets you do, it's a library for symbolic computation in Python, but it's also incredibly, it was built with neural networks and machine learning models in mind, and so it's incredibly useful for those. Basically, Theano lets you define equations in terms of variables, so you can define a few variables, call them x, y, z, define functions of those variables, y equals x squared, z equals x plus y plus z times 3, whatever. And then input numbers for those variables. And what Theano will do is, because you defined all of these functions purely symbolically in terms of variables, it will it has a backend where it will generate really high performance, like optimized C code for you. It will then compile that C code into a function, and it'll let you pass numbers into that function, and then you can evaluate whatever the outputs of your function are in terms of those numbers. And this is useful because the models that we want to train often are pretty computationally expensive. And so doing them in raw Python tends to be slow. This is also useful because since Theano has like the full symbolic representation of your equations, it can perform a series of transformations on them, and it can actually like do things like differentiation of your equations for you. This will become pretty important later on. We'll get to that. And then, let's see, the third thing about Theano that makes it really useful is that your variables, it comes with support for a whole bunch of operations out of the box, not only on like single numbers, but also on vectors and matrices. And depending on how far we get in this talk, those may come of use, because a lot of neural networks are implemented these days basically as giant matrix multiplications. So that's Theano in a nutshell. I'm going to give you, hopefully, a short introduction on how that stuff works. So we're going to import Theano. And Theano has this little utilities library called Tensor. And so we're going to import Theano Tensor as well. And we're going to go ahead and define some stuff. So I mentioned Theano lets you define symbolic variables. So we're going to go ahead and define some. I'm going to define one called x. Actually, let me talk about the model that I want to build first. We're going to code like a very, very simple machine learning model right now with Theano. And that model is just going to be basic linear regression. Given a series of points that is xy coordinate pairs, we're going to see if there's a line that fits those points really well. And the specific model we want to do is like, say the actual line we're trying to fit is like y equals 2x plus 3. So that's what we're going for. But we're not going to tell the machine that. We're going to see if the machine can figure that out on its own. So we're going to define some symbolic variables in Theano. That's how you do that. And x will be the input number that we feed in. And our model is going to be y equals mx plus b, which is just a line for some given value of m and x. This means we also have to define m and p. And we're going to use something called shared variables here. They're somewhat complicated to explain, so I'm going to gloss over them for a bit. But basically, they're what you do if you need to have a variable that persists its state between multiple instances of the function. So what we're doing is we're defining a function which has inputs and outputs, but that function also has a few parameters which need to be saved in memory. And so whenever you have parameters of a model, basically, you can think of it as put those in Theano shared variables. So we give it some default initial value, and then we say Theano.shared. The other thing that we need to do is we're actually going to have two y values. This is going to be called our y prediction value, or predicted y. And then we're also going to have a y target, which is going to be an input. And the reason for this is that, again, we want our model to learn from a bunch of data points we give it. And so at each step, we're going to give it an x, and we're going to give it a target of y. We're going to have it predict what it thinks the y should be for a given value of x. And then we're going to have it update itself based on its error. And this means, of course, that in order to figure out how it has to set m and b, we need to define some sort of cost function. And this is basically a measure of how wrong the neural network was on a given point. These are pretty standard. In statistics, the one that's typically used for linear regression is called sum of squared error. This literally just means we take our y target, subtract our y predicted, and we square the result. Straightforward enough. And what'll happen is we're trying to make this cost number go as far down as we can. We're trying to minimize it. And as you can see, the cost function is going to be minimized when y predicted equals y target. So we're going to tell our model to, we're going to tell Theano to figure out the values of m and b such that that cost function goes as close to 0 as we can make it. And the way we do this is actually pretty clever. It's a technique called gradient descent. And gradient descent is sort of important, actually. It's the algorithm that powers a whole lot of like, we're using it right now to train linear regression, but gradient descent is an incredibly simple, but also incredibly powerful algorithm, because all of those really complicated neural networks that I just showed were all trained using basically variations on this same method. And the way it works, for reference, how many of you guys like remember like basic high school or freshman college calculus? Okay, cool. So you have, let's see. You have a function, let's call it y equals x squared, and you want to minimize it. And the one way that you can minimize a function, specifically, that is, I'm trying to find the x value for which the y value is least. And one algorithm for doing that, that is gradient descent, is basically what we're doing is we pick a random y value. We calculate the derivative at that point, which is the slope of the tangent line at that point, et cetera, et cetera. And what the derivative at that point is going to tell us two very important pieces of information, which is, one, which direction do I have to go in x in order to increase or decrease y? If the slope is positive, that means that if I increase x, y is also going to increase. If the slope is negative, that means that if I decrease, or if I increase x, y is going to decrease. And then the other is how steeply that happens. And so gradient descent can be simply stated as pick a random point, figure out the gradient at that point, and then pick another point that's a little bit far, like just a little bit off from your original point in the opposite direction of the gradient. So to give you an example, if I were to do gradient descent here to figure out the minimum of y equals x squared, I can pick a random point, figure out the slope, go in the opposite direction of the slope, which means like take a little step in this direction, go down here, and then repeat. And eventually I would converge on that point, which is exactly what we're trying to do with our cost function. And we're going to code that up in Theano in a second. But one thing that sort of requires is jumping into calculus a little bit and actually figuring out the symbolic representations for the derivatives of this little cost function that we defined, and then of the linear regression and all of that. And this is why I think Theano is actually so cool, is because it has access to the whole symbolic graph of your computation. We don't actually have to do any calculus because Theano includes an automatic differentiation engine, similar to, say, the one in Wolfram Alpha or what have you. And so it'll figure out our derivatives for us. We just have to tell it what we want. The two derivatives in this case that we care about are the derivative of cost with respect to both of our parameters, because these are the things we're actually going to try to change. So I'll say dcost dm equals, and this is Theano syntax. And then now we have our derivatives. So we're going to go ahead and define a train function. And this is just Theano's way of defining functions in terms of things. A function has inputs. In this case, we have to give it an x value and a y target value. A function has outputs. In this case, we want, say, we want the prediction, we want the cost, we want m, and we want b. And remember I said, like, Theano shared variables are variables that sort of have memory across function calls. Well, this is basically what that means. every time we run this function, we're going to also tell it to update our m value and our b value. We're going to tell it to update m to whatever the old m was.
Excuse me?
Yeah. Sorry.
Okay, so for d cost dm and d cost
Yeah.
db, are those like the derivatives or what are they exactly?
Yeah, that's the derivative of the cost with respect to m, and then the derivative of the cost with respect to b. Because if you think in generic terms, I gave you like the little graph was a two-dimensional example.
Yes.
But we're basically trying to minimize a function in terms of some other variables that are inputs to that function.
Okay.
And in this case, we're trying to find the values of m and b that are going to minimize cost. And so we figure out the derivative of cost with respect to those, and then we're going to move those in the direction that minimizes that cost.
Okay, so what is m and b?
M and b are the slope and y-intercept of the line.
Okay.
Linear regression as a model is basically just trying to fit a line to all that data.
Okay.
And so
you need like 2 in order to like diverge to until you minimize the error.
sorry, not sure what you mean.
Okay, so wait, you need those 2 in order to actually like get the slope of line to equal 0 in terms of like minimizing the error cost.
You're trying to get the cost function to equal 0 if you can, and in practice, your cost function will never equal 0 because your data is a little bit noisy. But the data that we're going to feed into it is going to fit pretty well to a linear model that can be described as just y equals mx plus b.
Okay.
Because we're going to randomly generate this data to fit that model explicitly.
Okay.
But all of the stuff that I'm talking about can be applied to models with any set of parameters, really. It doesn't have to be a line in terms of a slope and an intercept, and hopefully if we have time soon, we'll get into more complicated models.
Okay.
So anyway, this line here is basically gradient descent. We take m and we set m equal to m minus the derivative of that cost with respect to it, times some small number, because we want to take small steps in the direction opposite the direction of the derivative. And then I'm going to do basically the same stuff. And in theory, that's all Theano needs to know in order to train this model. So we're going to go ahead and we'll train for 100 steps. And at each step, I need to import a random number generator. At each step, I'm going to pick a random x value between 0 and 1. I'm going to calculate my y value. I believe that's what it was. Yeah. And I'm going to pass into train my x and my y value. And remember, what the model is going to do is it's going to calculate its own y value. It's going to compare that to the correct y value, and it's going to update itself. And along the way, it's going to return its prediction for the y, the current value for the cost, and the parameters m and b. So we'll see how this thing trains. Oh, one other thing that I sort of glossed over. The algorithm that we're applying is actually called stochastic gradient descent, because the actual cost function that you're trying to minimize, in theory, is the sum of squared errors over the entire set of possible inputs you could ever give it. But obviously, that's very computationally infeasible. And so instead, what we do is we pick a random input, we train it for a little while on one random input, and then we pick another random input, and we train it for a little while on another random input. And obviously, the gradients for all these inputs are going to be very different. But if you keep on shuffling your inputs and only train for a little bit on each one, turns out all of the differences in the gradients cancel each other out basically as noise, and you're able to train the network as though you were training on the entire set of possible inputs. And this is a pretty good, very computationally feasible approximation to that. So anyway, we're going to run this, and we're going to see how it does. Oh dear. can't multiply sequence by non-int. Oh, of course. I think I have to explicitly specify some stuff. Oh, no. Ah, my bad. Small syntax mistake with Theano. If you're following along, lines 17 and 18 should not have parameters wrapped in arrays. And so we'll run this, and oh my, that's a kind of a mess. But let's take a look. So for each line, what it's going to print is first its prediction, which is to us a random number because we don't know the input, and then its values, and then its cost, and then the values of M and B. And so you can see it starts out with the default values we gave it of 1 and 0, and its cost is 12, which is pretty high, 12.6, and then 12.9. But by iteration 3, the costs get significantly lower. Now we have 8, 11, 7, 10, 7, 8. There's a lot of randomness. But if you look at M, you can see it's slowly going up from 1.0 to 1.08. By the time we get down here, it's 1.2. And likewise, our B value is going from 0 to 0.7 to 0.14 down to 0.5. And if we let it train for 100 examples and scroll all the way to the bottom, we find that it managed to get a Y value of 2.2 and a B value of 2.5, which is not bad because the actual values we were going for were 2 and 3. I wonder what happens if we let it train for like 1,000 examples. And we can do that because we'll be fast. It gets 2.1 and 2.9, not bad. We do it for 10,000 examples. 2.000 something something and 2.999 something something something. Pretty good. As you can see, gradient descent managed to converge on the correct numbers for a pretty trivial problem. And this is basically how we train neural networks and how Theano works. Now I'm going to jump all the way back here and talk about what neural networks sort of actually are. So to motivate building neural networks, we have all these problems in our world that are incredibly sort of difficult in the sense that we've tried building algorithms the classical way to solve them, and those algorithms have had pretty awful accuracy, to be honest. We've tried to do image recognition this way. We've tried to do handwriting recognition before that, speech recognition. All of these are problems where we have very, very complicated relationships between pieces of data, and we need to figure out those relationships in order to, say, figure out if an image is a cat, or figure out what a person is saying in a certain audio clip, stuff like that. And prior to neural networks, all of the algorithms that we had for these things were pretty poor performing. But at the same time, we knew that an algorithm existed that was capable of solving these problems. It's not just that they're unsolvable problems, because we have an existence proof in the human brain, right? Like, we can solve these problems pretty darn well. Therefore, there must exist an algorithm. We just don't know it. And so it makes sense not to completely ignore neuroscience. And if you don't completely ignore neuroscience, you find out that your brain has this sort of structure where different groups are, hey, what's up? Are you just stretching? All right, cool. Got it. If different sections in your brain are responsible for handling different tasks like vision and speech and processing language, basically all the things we're trying to do. But if you look at the neural anatomy of those sections, you find that they all share this sort of uniform structure where you have neurons that are hooked up in sequences called cortical columns, and then those cortical columns are arranged into what are called groups, and information flows from one group to another group to another group through these cortical columns. And very interestingly, the whole this whole structure is the same from the vision center of your brain to the speech center of your brain to the language center of your brain. And not only are they anatomically very similar, but there have been studies done on people who have unfortunately received trauma to one or more of these areas, and you find out that if, say, a portion of the speech processing center of your brain, or the center that used to process speech, gets damaged, other parts of your neocortex can sort of pick up the same functionality and learn that same task pretty quickly to compensate. And this suggests that, like, basically any portion of this structure of your brain is able to do any of these tasks, which strongly suggests that rather than there being separate algorithms in your brain for speech and vision and all of this stuff, that your brain has one sort of generic learning algorithm that's capable of extracting meaning and building structure from all of this raw, really noisy input. And so neural networks are sort of a vaguely biologically inspired attempt to figure that out. And they work as follows. So the basic building block of a neural network is this little thing. We'll call it a perceptron. That's technically not accurate, but whatever. And in diagrams, it's usually drawn this way. Literally, all a perceptron is a pretty simple function where you take one or more inputs, in this case, say x1, x2, x3, and you multiply them by one or more values. We call them weights. And you'll multiply, like, the first value with the first weight, the second value with the second weight, the third value with the third weight. You add some random value called a bias, and then you pass all of that through some function that is nonlinear. In this case, I'm using the tanh function. It looks like this. It's convenient because it's basically like a differentiable approximation to a step function. Remember the whole gradient descent thing we talked about earlier? Well, one of the key requirements of using gradient descent is, like, your function, your neural network, or your linear model, or whatever it is, every step, every computation you do there has to be differentiable because you need to calculate those derivatives. And so this is just sort of a smooth differentiable version of a step function where, loosely speaking, you can think of a perceptron as it takes some inputs, it weighs those inputs against each other, and it makes a decision based on that. This isn't exactly how they work, but you could think of it as say, like, you build a perceptron to make a decision on whether you should go to a cheese festival one day. And you might have inputs such as, like, is it raining today? Does your best friend like cheese festivals? Are you really into cheese? And you'll feed those in as numbers, and you'll weigh them relative to each other. And you'll come up with a decision, yes, I should go to the cheese festival, no, I shouldn't go to the cheese festival. So a perceptron is like a really simple model for making pretty basic decisions on the basis of inputs. And if one perceptron can make reasonably basic decisions like this, it stands to reason that maybe a complicated network of a lot of perceptrons can make more subtle, more complicated decisions. And so if we take a bunch of perceptrons and we wire them together, then maybe these perceptrons will be making some sort of decision about the input, and then these perceptrons will be aggregating those other decisions to make sort of more complicated, subtle decisions. And we're going to have all of these little decisions being made along the way. And in fact, this is vaguely similar to how it's thought your brain does it. Where in your brain you have neurons, and those neurons are all hooked up to each other via synapses, and a neuron takes some input in the neurons that connect to it, and either fires or doesn't fire, and these firings propagate through this giant network, and computation happens, and you get some sort of output. So this is a pretty common neural network model. It's called a multi-layer perceptron. You can see the perceptrons of this diagram are organized into layers or like vertical columns. And what happens is you take your inputs and you put them here, and the inputs then flow along these arrows and are multiplied by some weights to this layer of perceptrons, which sort of transform those and make decisions in terms of the inputs. And then it flows on farther to another layer and then another layer. In this case, there's really only like one layer between the input and the output. But you can have arbitrarily many layers. And the more layers you have, obviously, the more refined decisions you can make, the more complicated correlations you can figure out. But eventually it makes it to some layer of neurons that we call the output, and then we read the values at the end of those neurons, and we interpret them as like something. So here's a quick hand-drawn example of how you can use neural networks to calculate basic functions. If any of you are familiar with the XOR function, this is a neural network that can calculate XOR. The weights were figured out entirely by hand. And it's really just meant to give you a sort of proof of concept of how you can use this thing to do reasonable computation. So you pass in two values here that are either 1 or 0. You propagate them along to those 3 neurons, at each step multiplying them by 1. You add them together, and then the values at those points are going to be those values. And then you multiply them by those things, and you pass them in there, and then you get an output there. And if you pass in like 1 and 0, you get 1, and if you pass in 0 and 1, you get 1, and if you pass in 1 and 1, you get 0, and if you pass in 0 and 0, you get 0. And this is basically just what that function is supposed to do and how you can implement it in terms of neural nets. Let's see, do I go there? I think I'm going to, yeah, I may as well. So one way to think about how neural networks work with these series of layers of neurons is that at each layer, you're taking all the information from the previous layer, and by passing it through a set of perceptrons, you're transforming it into some other representation. You're figuring out another way of looking at the same data. And as the data passes through multiple layers, it gets transformed into ways that look easier and easier to classify. And to put this into slightly more mathematically rigorous terms, each layer performs basically some sort of deformation on the layer before it, like some sort of continuous but nonlinear deformation of the previous layer that makes the data more separable. So this is a data set that was fed to a toy neural network, where we basically have a red line and a blue line. And the task that the neural network was given is, given a point on this graph somewhere, classify it as belonging to either the red line or the blue line. And a really simple neural network with only like 1 layer and 2 neurons will try to classify the points on the graph like this. It'll basically try to find a line that separates the data. And you can see it doesn't do too well, because there's like some parts of the red line that's still in the blue region and vice versa. But it did a reasonably good job at separating most of it. And then if you look at a slightly bigger neural network, that is one with 3 neurons, I believe, you can see that it does an even better job of classifying this data, because it's able to like figure out a nonlinear way of separating them. And one way to think about what's actually going on here is to look at not, right now we're looking at sort of the inputs we're giving to a neural network, and then what they get classified as. But we can actually look at, instead of the inputs, going back here, instead of graphing like these 2 values, we can instead pass these 2 values in and graph these 2 values. And we can see what the neural network sort of sees as its internal representation of this problem. And this is the same exact neural network, but now we're just looking at what are called like the hidden neurons. That is just the neurons that are in between the input and the output. And we can, the axes and the lines are actually the same lines. It's just now in a different coordinate set. And we can see that the neural network learns basically a way of warping and transforming this space into this space such that the things are now linearly separable. Here's another example, except this time we're going to animate it, and we're going to see how this deformation actually occurs. So right now, like if you tried to fit a linear model to this data, there's no way you're going to be able to separate the blue and the red line from each other, because they're all entangled. But it turns out there's a transform that you can do, where if you stretch it a little bit and then do some other stuff, this was all figured out by neural networks, but you transform the data in such a way that now you can like easily draw a line through it and cut the blue apart from the red. So that's that. And now we'll get into implementation stuff. I mentioned before that neural networks tend to basically just be large series of matrix multiplications. Well, this is kind of what I mean. Instead of thinking of each perceptron individually as a unit, if we think of all the perceptrons in a layer as a like unit, then what we see is like, you can think of this rather than being 4 separate pieces of 4 separate numbers as a vector of numbers with length 4. And then you can think of this as being a vector of numbers with length 5. And the operation that you're doing actually to get from here to here is basically just matrix multiplication. I can go through the mechanics of it, but basically like the first set here is these 4 numbers multiplied by 4 weights, and then this is another 4 numbers multiplied by 4, the same 4 numbers multiplied by 4 other weights. Basically, you're taking this vector and multiplying it by a matrix of weights, where the columns in your matrix correspond to the weights for individual output neurons or output perceptrons there. And so if you do that matrix multiplication, it's actually the same computation as just doing this formula, except without the tan h, just the weighted sums. For every individual neuron here. And when you write it in matrix form, it's just a lot simpler and less loopy. And then once we have that, we can just take each element of the vector and apply tan h to it. And then we get the outputs for our first layer. And then we do the same again to get from that to the output layer. And now we get to jump into code again. So let's see. We're going to change our model. Oh dear. We're going to keep x and we're going to keep a target y value, except instead of an m and a b now, we're going to have weights. And I'm going to import NumPy. And we're going to have some biases. And what I'm doing here is I'm just initializing the weights and biases as first a 1 by 5 matrix, and then the biases are just a vector of length 5. And they're going to be our parameters for this little toy neural network. We're going to have y predicted equals. So first we're going to take our input. And then we're going to multiply it by our weight matrix. And then we're going to add our biases. And then we're going to take this whole thing and pass it through a tan h. Actually, tell you what, we are apparently 5 minutes from the end of this talk, so maybe I'm not going to go into this demo, quite unfortunately. But if any of you are interested, I can show you code online later. I'm happy to walk through it. But it might be more useful right now just to keep going through this stuff, because that's a reasonably good explanation of how that works. Anyway, so if I were to have gone through that demo, and if we had time for that, turns out you can build reasonably sophisticated models just like this is sufficient complexity to model a lot of interesting things, like handwriting. If I pull up, let's see, do you have the wrong version of this thing here, but here we go. So if you look at like handwritten digits like this one, this is a pretty complicated problem to model just in terms of like a non-learning algorithm. And in fact, even like other machine learning algorithms, for instance, logistic regression or like clustering or whatever, tend to have a little bit of trouble on this because there's like a lot of little variations in the way people do handwriting. And so figuring out what these digits mean, although it's pretty simple to you or I, is actually not a trivial task if you want like really high accuracy. Neural networks can achieve something like 99.9% accuracy on this problem. And it's all just variations of this. Specifically, if you take each of the pixels of that input image and code it as a grayscale value, like a float between 0 and 1, pass it straight into a neural network. This says 20 by 20, but those pictures are actually, I think, like 28 by 28 or something like that. So you now have 784 numbers. You encode your image as just like a sequence of 784 numbers. You pass it into a neural network that has 1,000 neurons in its first layer after the input, that is its first hidden layer. And then those pass them on to 10 output neurons. And you, like, each output neuron corresponds to a specific digit, and whether or not it fires or the value at which it fires determines the probability of the network predicting that digit. Turns out that alone is enough to get you to 98.6% classification accuracy, which is pretty darn good. And then you can build models like this, where you add a few more series of layers. And what you're actually doing at this point is you're doing a sort of computation in that, like, instead of learning like basic correlations between input and output, the level of transformation that you can do on the data is rich enough that you can actually make this thing do computation. And so it's learning like the same sort of algorithm that you would have had to teach it manually, just in a very, very different way. And then there are convolutional networks, which we don't really have time for, unfortunately. But the idea of a convolutional network is basically like, previously I told you that we had to take a 20 by 20 image or a 28 by 28 image and feed it in as 784 individual values. Well, the downside of that is that each of those values corresponds to different specific lines here and different specific weights. And so if the network learns like a certain image processing technique, it has to learn that same image processing technique for every single little patch along the image. Every combination of weights and biases and such is independent of every other one. Convolutional networks are basically a clever little trick where they learn to do computation on small little overlapping patches of the image, and that computation is done, like it's basically looped over the entire image. And so any computation that they learn applies to the entire image. And that is surprising or unsurprisingly basically exactly how our human visual cortex does it, where we have this thing called the V1 cortex, where like raw light information from your retinas basically comes in, and there are all these neurons that pass it through these filters. And if you look at the pattern of synaptic activations for each of these neurons, you get these very like distinctive patterns. And this is something that I think is really cool, actually, because if you look on the left, this is like we like took fiber optic cables and stuck them in neurons and figured out the patterns of firing. And these are like sort of like the little rectangular patches of light that will trigger firing in certain V1 neurons. And on the right, you have the equivalent patterns that trigger firing for neurons in the first layer of an artificial neural network. And what's cool is if you look at like at least the top half of those filters and then these, we got stochastic gradient descent to basically figure out this little technique for detecting edges in pictures that is more or less the same technique as the one used in our brain, except we never told it that. It figured that out entirely on its own, which I think is pretty cool. And that's all I have. Hopefully, like now you have some idea of how these models work, and also why I think they're cool. If any of you guys have questions, I'll probably be around for a while. But other than that, thanks, guys. That's all. Yeah.
For the weights, how do you get the weights? Like, do you go through testing process?
Gradient descent. I'm not sure if you were around for that part, but basically the idea is you start out with a series of random weights, and then you try an example on those weights, and then you calculate a function that determines basically how off you were from the correct result. And you use calculus to figure out like which direction do I have to tweak each of these weights in to make that cost function go down. You tweak it, and then you repeat on another example. And you keep doing that and doing that and doing that, and eventually you get a set of weights that like makes your network do something useful. Did you have a question or?
I forgot my question.
All right, no worries. Yeah.
So is there some sort of trade-off in this increased accuracy in your networks? Is it more computationally expensive, or it's just?
I mean, there are a lot of factors that you can tweak to increase accuracy, and the larger your model is, the more weights you have to store, and also the more weights you have to compute each time. And these things do get pretty computationally expensive. Like in the demo, we talked about like neural networks with like a couple thousand little neurons connected to each other. Google has at this point trained neural networks with like, let's see, maybe 2,000 neurons times 20 layers is 40,000 neurons, is like several billion synaptic weights between them. And at that point, you need like clusters of dozens to hundreds of machines with GPUs, each with like hundreds of processors running in parallel. And that gets unwieldy pretty quick. And so the main bottleneck, in fact, the thing that's caused neural networks to grow so tremendously in popularity and accuracy over the past 5 years, mostly has just become like, it's basically just been Moore's law. Our processors have gotten a lot faster, and so now we can build neural networks that are a lot bigger, and consequently we can do a lot more. We're still like a couple decades of Moore's law away from being able to simulate the same number of synaptic connections as is in your brain. But it's also not clear whether we need that number in order to do a lot of useful things. Like even with the computational capacity we have today, we can do a lot. And it's pretty clear that like if we just take the same algorithms we have today and scale them up to like 10 times as many neurons, we're going to be able to solve a lot of problems that like today were intractable. It might be the case that like full artificial general intelligence of the kind that's talked about in sci-fi movies and the kind that we consider to be the holy grail of our field is literally just a matter of taking the same algorithms we already know and throwing like 10 to 100 times as many neurons at it. It's something that we speculate, and that might actually be true. We just aren't entirely sure. But again, mostly computational cost. Yeah.
Do you have any tips on improving one's skill from this point in applying and creating neural networks?
Yeah, for sure. Read a bunch. So one thing, like, the way I got into this was I was interested in one very specific problem, and that problem was speech recognition. I was interested for a completely different reason. And for the longest time, neural networks seemed like this sort of like really opaque, difficult to understand thing for me. And I was really into speech recognition, and so I looked up like, well, what's the state of the art in speech recognition? It was this paper, and it was full of jargon, and I didn't understand it all. But I kind of just like kept going and understood what I could, and then I read the references on that paper, and then I read some introductory stuff about neural networks. And very quickly, like within a couple weeks, you find that like there's actually like, it's a surprisingly new field, and people know surprisingly little. And so it's pretty easy to catch up, at least in one specific niche. Like for me, recurrent neural networks and speech recognition, it's pretty easy to catch up to the state of the art. And especially recently, there are like a ton of resources that have been published. I can refer you to like books that are pretty accessible for beginners and such. But it's pretty easy to catch up to the point where you're able to like read new papers as they come out, and when you're reading new papers as they come out, you slowly sort of develop an intuition about these things. And then once you've developed an intuition about these things, you're able to like propose experiments and come up with applications that actually push the state of the art further because there's stuff nobody else has thought about.
Okay, yeah. Okay, so I've been like trying to learn stuff like machine learning and networks for a while. And the thing is that I know a lot about the theory, but I have like so much difficulty on like trying to program or apply it to any type of thing, like getting started on a first project involving neural networks.
Do you have projects that are interesting to you?
Well, I do have a few, like such as like perhaps something with computer vision, or something in like something as simple as a spam classifier.
Yeah. Is your difficulty in implementation that you find these things particularly like hard to implement, or is it that you don't know where to start? Or
like I do
like,
know how to start, because like I know that there's like a series of sequence in order to like make a simple neural network, and I try to create my own. Like I even like try to download some kind of scikit for Python, and then apply documentation. I once tried starting from there, and I could get the documentation to work. Yeah. But if I like apply other data to it, I end up like getting a ton of errors.
Try. Let's see. I would say try Theano. So Theano is cool for two reasons. One, it doesn't sort of like hide the model from you, right? You get to build your own model from scratch. But two, it pushes, like it does a lot of heavy lifting for you. You don't have to write your own like linear algebra routines. You don't have to write your own like differentiation and derive your own derivatives and stuff. And it also comes with like a pretty extensive series of tutorials that will cover like all the basics, like logistic regression, which is good enough for state-of-the-art spam classification, and all the way up to like deep convolutional networks for image recognition and stuff. They're just like beautiful, pretty easy to follow tutorials on Theano's website for going through that stuff. If you're interested, we can take a look at that stuff at some point later. But like, there's a ton of like, if scikit isn't working out for you, don't limit yourself to scikit.
Yeah,
right?
because I've been trying to like find other like kits, and not only just like kits, but also kits supported with kits supported with a lot of documentation to actually like learn all this stuff and actually get started on first project.
Yeah.
Because all I know is how to actually like copy and paste code that will fulfill that documentation. But if I like try to tweak it or modify it in any way, such as like adding my own code or basically like using a new data set with the same algorithm, it ends up getting errors.
I mean, yeah, it in theory should work. Just one of the things about scikit is that scikit is a pretty big and complicated piece of code, and like it touches a lot of things, and so like you may end up running into errors there. And if you've tried a bunch of stuff with scikit and you don't like scikit, like try some other stuff and see how it works out. But there are a lot of machine learning libraries out there.
So Theano is like more beginner friendly.
I wouldn't say that it's
like I know
specifically much better for implementing neural networks.
Okay.
And it does a lot less for you, which is in some ways like bad, because now you have to write your own code to say like do training and validation sets and cross-validation and stuff. But in some way good, because you're less like your problem is less like how do I understand the scikit documentation, and more like how do I build this stuff from scratch on my own, and you sort of get a much better feel for how everything works behind the scenes when you're building it yourself. And if you're comfortable in Python, like then all of this stuff is stuff that you should be able to build without relying on scikit too much. Yeah.
2 questions. First,
sure.
Is there a way you can make your demo source code file available to us?
Yeah, of course, sure.
You have a GitHub?
GitHub or something. Second question?
Second question. For your increment variable, you used a constant number. That was very small.
Yeah.
Is that what we usually see, or is it common to use a dynamic?
Oh, heck no. There are all sorts of dynamic ways for setting those and setting those differently for different parameters. So the variable you're talking about is called the learning rate. And I can go through a few basic ideas for setting that learning rate. It works like well enough to pick some reasonably small number. But like obviously if you pick too small a number, your network will learn very, very slowly. And if you pick too big a number, what will happen is it'll actually take steps that are too big and it'll overshoot its goal, and then it'll have to go back and it'll diverge, it'll go all over the place. So my
thought was like, for example, like for a missile targeting system, like where it has its target and like it's just continuously reevaluating where it is, right?
Right.
So it starts very far on one side and then very far on the other side, and then eventually like getting it closer, 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 closer.
Right. That's more or less exactly what happens, or what learning rate schedulers. So there's this thing called learning rate scheduling, where basically as your network trains, you take that learning rate and you start it off as a high value because you want to move like really quickly. And as you get closer to your target, you exponentially decay the value of that learning rate so that you take smaller and smaller steps and you start converging in on your target. Another common strategy that's used is actually, so one way you can think of gradient descent in general is like, you're kind of like, your cost function is sort of this surface or this curve, and you're rolling a ball down the curve to try to find the minimum. At every step, you basically move in the direction that is immediately downhill, and you keep moving downhill and you eventually get to the minimum. Right. Well, it turns out you can take this metaphor and actually like implement it a little more literally in the algorithm. Because balls rolling down hills have like a certain amount of momentum to it, where instead of just like moving it in the downhill direction, you have like an acceleration in the downhill direction and a velocity, and the ball travels according to its velocity, and the hill only affects the velocity indirectly through some acceleration. And by giving the ball some momentum, what you do is actually you make it so that like if there are small little bumps and ridges in your surface, the ball will kind of just skip past those because it has so much momentum. And this is actually really useful, and turns out, for whatever reason, it results in neural networks that train much better, much quicker, and to like higher accuracy than otherwise. There's like a ton of tricks that you can do with learning rate scheduling, some of which are pretty rigorously backed by mathematics, and there's a lot of papers. Others are just like, well, we tried this weird thing and it worked really well. But yeah, it's like a pretty big area of research.
So obviously the target goal for manipulating this variable is to get the smallest amount of trial cases before you get an accurate result.
Exactly. You want to train things as quickly as possible. Yeah. And it turns out like it makes a huge difference. Like there are certain problems with certain neural networks where it's not just that it will train quicker if you use the right learning rate scheduler, but like it will completely refuse to train at all unless you have the correct algorithm for manipulating that number just so. So for example, the momentum problem that I mentioned earlier, you might have let me see if I can, I won't go into it because it'll probably take a while. But there are certain cost functions that are incredibly difficult to solve without the right learning rate algorithm. Right. Yeah.
APIs. What do you think? You know, if you would work on something like, for example, you take a picture on your phone of a piece of paper. You want it to read everything on the page. What API would you use for that? If there's anything available.
I should probably throw in a quick plug for this. I work at a company called MetaMind. Yep. Our product is an API that does neural networks and deep learning. Right now, we support two basic, and we support a few more than two tasks, but I'll talk about two. One is image classification, where let's see, here's a little toy demo of one of our APIs for classifying food, where you pass in an image of a food and it'll tell you what kind of food it is. We also have, let's see, a semantic similarity model, where you give it two sentences, and it'll tell you how similar the meaning of those two sentences are, independently from the actual words. As a number between 1 and 5, where 5 means like perfectly similar, and 1 means not related at all. We also let you train your own classifiers, so like you can give us a bunch of text and a bunch of labels and say like build a classifier based on this training data, and we'll do it. We can do the same thing for images, and on all the things we do, we are state of the art, which is to say like our models perform equivalently or better than anything you will find in literature or industry outside of us. Let's see. We have some weird Twitter stuff. We have a general classifier which you can use, which is like the food one, except it can classify things that aren't food. Anyway, we have a number of models, and there are a number of companies other than us that have a number of models. To answer your specific question, optical character recognition is probably not something that like I'm pretty sure Google has a free API that can do this. Google OCR API. No. Anyway, the general problem you're talking about is called OCR, optical character recognition. And so if you Google like free OCR API, you find a ton of stuff that I'm sure is able to do it. And if like, is this something you're working on this weekend or
we're still looking for ideas.
Sounds good. Yeah, if at any point you
is
need
it like as good
to work,
because you said like it's 96%, so it's as good as that.
I have no idea. I literally just found this on Google. But you know, if you're planning on using it at any point this weekend or afterward, and you want help trying to pick one or figure out how to get it to work, regardless of whether you use MetaMind stuff, you know, happy to help.
Where can we find you?
It'd be useful.
LinkedIn.
I guess LinkedIn, but I can like here. You can email me. My email address is ishan@metamind.io. Don't email me because I don't shoot. Here, I can give you my phone number, and then you can call me or text me at any point in the future that you want, and I can try to be super helpful or maybe not.
All right, good.
Yeah.
You mind if you share your number with me then too?
I'll just put it on the screen. All right. Probably easier. Yeah, no, of course.
How was your Ruby?
Huh?
How was your Ruby?
See, kind of.
I can help you guys with Ruby too, for what it's worth. Great. Cool.
Also, a random question.
Yeah.
Did you complete all your schooling in the States?
I did 1 year at MIT in Boston, and I actually dropped out. So formally, I have very little schooling, and what has been done, yeah, was in the US.
How was MIT?
I mean, it was really fun. I'll be honest, I actually didn't learn that much. Probably one of my bigger regrets in life is that the 1 year I spent at MIT, I spent under the assumption that I was going to graduate. And consequently, I front-loaded a ton of boring introductory classes that I mostly already knew the material to. And so basically all of the interesting stuff that I've ever learned has been like self-taught, picked up along the way kind of stuff. Had I stayed there for longer, I probably would have learned a bunch of interesting stuff though, and I have friends there who like it a lot. Yeah, anyway, I left after a year to go do a startup, and then I spent a couple of years doing that, and then I got into AI, and that's what I've been doing recently.
That's awesome.
Just curious.
Yeah.
I have a friend, his name's Shard.
Yeah, I know.
You know her?
Of course. I love her.
Tell me about him. I haven't seen him in like 13 years.
Really?
Yeah, he's a childhood friend.
Oh, wow, really? Cool. Where?
Barely. Saudi Arabia.
Right.
Did he tell you?
Yeah, he's definitely told me, and I've definitely forgotten. It was either Saudi Arabia or Kashmir, and I forgot which one.
No, Saudi Arabia.
Cool.
Yeah.
That's awesome.
No,
Have you have you guys seen each other over here at all?
No. He lives too far away.
Oh man.
I know he's doing well.
Come to more hackathons. He's at basic. I'm surprised he's not here.
Exactly.
He's
I wanted to surprise him.
oh,
Yeah. I wanted to surprise him.
yeah,
I'm surprised. He's the one who told me like hackathons out.
yeah. No, they're pretty great. I love Sharif. He's a pretty amazing person. Did you have a question, or were you just like this?
If you want to like get in terms of like leading, let's get work in machine learning and neural networks. If you want to, I'm like more of a like trying to like start a project from scratch and then learn all the way.
Yeah.
How would you get started on that? Because I've been having a hard time like finding some tutorials that would help students hard that kind of learning style.
I can certainly recommend tutorials for you, but more like
Basically,
on a deeper level than that. Do you have a project that like you're particularly interested in or care about? One of the things I've noticed, at least about myself, this may or may not transfer to you or other people, is that I learn best when like
keep all the relations.
at least when I'm doing like the do it myself, like figure it out along the way, work on project style learning. I work best. Like there are two possible outcomes when you're learning. Right? Either you succeed and you learn, or you give up somewhere along the way. There's no like outcome other than either you give up or you succeed. And if you're sufficiently motivated, you probably feel like that helps to avoid giving up at times when otherwise like you hit roadblocks and things get really confusing. And to that end, I think I learn a lot better when the project that I pick is something that I'm
There's no way to do it.
Yes.
There's not.
So if you can find like a project that you really care about for whatever reason,
Unless
just be like interesting or meaningful to you somehow.
Yeah.
I can certainly like help talk with you about like architectures that you might want to use and tutorials and give you all sorts of starting points, either now or later, or because you have my phone number.
Unless you make it.
Well, the main motivation is either something in computer vision or natural language processing.
Natural language processing is really, at least the stuff that I touch, which is neural networks for natural language processing, is actually really cool. So are you familiar with the idea of a word embedding?
Are you talking about like a grouping each word, set words, or?
I don't think so. I'm talking about like associating each word with a point in a like say 100-dimensional vector space, such that words that are semantically similar are closer together in this vector space.
Okay.
And that was a whole bunch of words, some of which were pretty jargony, and I apologize for that. But basically, you can use neural networks to learn,
It's just like you just keep it
to like figure out relationships between words in such a way
and based on
that
the taking class,
like you can use them to solve analogy problems. Like if I were to say like man is to woman as king is to, or you can get a neural network to tell you the meaning, and all of the like associated knowledge you have to figure that out. Just by like looking at massive amounts of text, and the models which we use to do those are called neural word embeddings. And they're a pretty straightforward model to understand. I can show you some videos on that, and there's a whole bunch of tutorials on that for yourself.
Trust me, I've done this before.
So that's one cool thing
I've done the exact same thing
in that field. I don't know if there like a specific problem that you're trying to solve, or if you just want to play with stuff, I can certainly basic tips on that.
I think one course leads to
I'm
a
trying
bunch
to
of
like
courses.
teach myself like I want to like continuously build my knowledge in neural networks and machine learning by working on a series of small projects and I eventually tackle a complex one. In fact, basically like when I like learned the web development, I was effectively able to like learn web development at an exponential rate because I had tutorials that were able to like help me like do some simple exercises so that I have the intuition and enough knowledge to tackle something as complex as a social network kind of thing.
Yeah,
but
unfortunately, like I cannot find any
going to be just like in the code or
So there's a bunch of stuff that I can recommend. Some of it is more theory, some of it is more practice. Some of it does a reasonably good job of striking a balance. If you want stuff that's like more heavily geared towards the practice end, take a look at Keanu's tutorials.
Okay.
And give those a shot. Like skim through them, tell me what you think, and based on how those do.
Reading. I want to listen to your question. Like if OCR, basically it's just like students on Canvas can share notes.
Piano documentation.
Deeplearning.net is Piano's website.
Okay.
Or it's a website that's associated with Piano, I think. Or maybe it's not.
And the notes is like under your name.
Deeplearning.net.
You want to upload the entire branch, just like the series.
Will not prevent them, but
Search Piano logistic regression.
provide something or to narrowly alert as to when seizures are.
But there we go. That one is already done. So this goes through. This was the demo I was actually going to do, but it basically like gives you code and teaches you how to do handwriting recognition, which is a pretty good first step for machine learning stuff. And then it's part of like a larger series of tutorials where this teaches you how to do logistic regression. And then from logistic regression, you can build like a 1-layer or a 2-layer neural network, and then they teach you about regularization and validation sets and stuff. It's pretty good. They try to explain all this stuff.
Yes. Also,